of a random variable with an emphasis on the binomial distribution. So what we're going to say is, suppose that we flip a bent coin, okay, or a weighted coin, whatever you want. And the probability of getting heads on this coin is not 0.5, but is instead 0.4, okay. From this you can infer, hopefully, that the probability of getting a tails is 0.6, okay. And what we want to figure out is what is the probability that if we flip this coin 5 times, we get 3 tails and 2 heads. Okay? So this is a little bit tricky to figure out straight off the bat. So what we're going to do is first we're going to look at a simpler version of this, where we're actually going to try to figure out the probability of getting this exact sequence of tails, 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 heads, heads. Okay? And this sequence, right, is just going to be equal to the probability of tails times the probability of tails times the probability of tails times the probability of heads times the probability of heads. So that's going to be 0.6 times 0.6 times 0.6 times 0.4 times 0.4. So we can write that as 0.6 cubed times 0.4 squared. Okay? But that gives us only the specific outcome of this order. But we know that there's a bunch of ways we could arrange this, right? Because we don't have to draw the 3 tails first. So how many ways are there that we could arrange this? Well, we have 5 slots, and we want to choose any 2 of the slots to be heads. So if we want the probability of 3 tails and 2 heads, then it's just simply going to be 5 choose 2 times 0.6 cubed, 0.4 squared. Now, you might ask here, well, why do 5 choose 2 instead of 5 choose 3? Couldn't we choose 3 slots to be tails? Yes, we could. And because of Pascal's triangle, right, 1, 1, 1, 1, 2, 1, 1. If we go down to row 5, you can see that 5 choose 2 and 5 choose 3 are the same. And that's always going to be the case, right? If we had 4 instead, and I had 2 or 4, 0, 1, 2, 3, sorry, 2 or 3. Same thing. If you go down to 6, right, 1, 6, 15, 20, 15, 6, 1. Let's say that instead I flip this coin 6 times, right, and I want 2 heads. Well, I either have 2 heads, 15, or 4 tails, 15. 6 choose 2, 6 choose 4. So these things are always going to be the same, so you can really use either one to get it, and it's going to be fine. Okay? And we could kind of look for a pattern here. What if I say, what's the probability of, getting 0 heads? Okay, if I say the probability of getting 0 heads, then that means I'm going to have 5 choose 0 times 0.4 to the 0 times 0.6 to the 5, since we're filling up 5 slots with tails. Probability of getting 1 head is going to be 5 choose 1 times 0.4 to the 1, because we want 1, 0.6 to the 4. So you can kind of see the pattern here, right? For the number of ways that you can arrange it, we have already done 2 heads now, and that's just going to be 5 choose 2. So this combination in the front gives us the number of ways that we could arrange this, and then these things give us the actual number of heads and tails that we want. So you can continue this down. You can see that kind of the pattern we're getting to is really that the probability that an event, let's say an event A, happens x times out of n, and we're going to say, that event A has a probability of p happening, just to make things easy, is going to be equal to n choose x, right, total number that we want, times the probability that A happens, which is, p, raised to the x power, times the probability that A doesn't happen, so 1 minus p, to the n minus x power, right? And if you go back and plug this in for what we just did, you'll see that this equation really works here, where we're saying, okay, well, each time we're saying, okay, this is going to be 0, 0, right? These x's are going to match, and you're going to have n minus x for the rest. So 5 minus 2 is 3, 5 minus 1 is 4, 5 minus 0 is 5. And again, this combination is just the number of ways you can arrange these things. this represents the number of times you expect it to happen, and this is the number of times or outcomes that you want it to not happen. Okay, so this is called, this looks a lot like a term in a binomial expansion, right? If you took something like a plus b and you raise it to the nth power, right? You have, let's say that n is equal to 3. You're going to have a to the third plus 3a squared b plus 3ab squared plus b cubed, where you're taking the combinations from Pascal's triangle, row 3, and you're decrementing the powers by 1 for the first term and incrementing them for the second term. And you do the same thing here. So x is a random variable, okay? And we say x is a random variable since you can't know which value it will take until you actually run a random experiment. So it's a little bit unlike other variables where, you say, I want to solve for a variable, we plug it into an equation, we solve for it, we're good. X is a random variable because you can't do that. You have to do an actual experiment before you can determine its value. But functions of random variables are actually possible to be well defined. So if we take this example, right, and we can you calculate the values for this is a horrible graph, but that's okay. So we have 1, 2, 3, 4, and 5, and the probabilities, if you calculate these out, are going to be, so you have 0.1, 0.2, 0.3, and 0.4. 0 is 0.07776, that's going to be like here. 1 is 0.2592, so it's going to be around here. 2 is 0.3456, which is here. And again, I'm getting these numbers just by multiplying these things and continuing the pattern, right? So P for 3, for example, would be, if I choose 3 times 0.4 to the third times 0.6 squared, and you can keep doing this for 4 and 5 as well. So for 3, if we multiply that out, we get 0.2304, which is going to be like here. And then for 4, you get 0.0768, so that's going to be like here. And then for 5, you get 0.01024, which is going to be like here. You can kind of see this shape. I'm going to try to make it look okay. And this shape that you're seeing, where it's kind of peaked over here, and then it's got a long kind of thin tail where the probability of it happening is really small. This is called the binomial distribution. Okay, and the binomial distribution is a special distribution that happens when you're doing something over and over again. You're doing a repeated thing, and there's only 2 possible outcomes that can happen. Okay. So, this is the probability, and this is x, and this is the probability that happens. So, an example, right, is here. I flip a coin over and over and over again. Each time, the probability does not change. It's always the same. Probability of getting heads is the same. Probability of getting tails is the same. They don't affect each other. They're independent. They're mutually exclusive. Everything is very nice. And there's only 2 outcomes. Even something like taking a test actually follows this as well, which you might not think of, but if you're picking answers randomly, even though there's, let's say, 5 options for each answer can either be right or wrong. So if you're doing a test, let's say there's 5 choices per problem, you're going to end up having a 25% chance of getting the right answer and a 75% chance of getting the wrong answer. So then you have 0.25 is correct, 0.75 is incorrect. How many ways can you arrange it for however many questions you want to ask? So you say, oh, well, I want 10 questions and I want to get 3 right. What's the probability of that happening? You would say, oh, well, that's going to be 10 choose 3 times 0.25 to the third times 0.75 to the 7th. So you're going to just kind of plug into this binomial distribution.